Hey friends. So today starts a shift in this big long functions unit. Sorry. The first section, or the first third, you might even want to say, of our unit was on radical functions and square root graphs and rational functions. Now we're switching into the second kind of portion where we're going to talk about polynomials. Polynomial functions, and then the last portion you'll remember is on function operations. Okay, so today we want to introduce just some general characteristics of polynomial functions, and a lot of this you already know. It's just that you did it in a very I don't know, tunneled way throughout grade 10 and grade 11. Okay, in grade 10 you focused on lines. Okay, so you looked at y equals mx plus b, and you looked at y minus y1 equals m times x minus x1. When you looked at ax plus by plus c equals 0. And those are all different ways to write equations of a line. And then you got to know certain things about the line just by looking at the equation. Okay, a line is actually a degree 1 polynomial, okay, because we name the polynomial based on the highest exponent we see. So then we moved in grade 11 to a degree 2 polynomial, which we all lovingly know as a quadratic. And you looked at vertex form of a quadratic, and you looked at the standard form of a quadratic. You knew that the y-intercept in the standard form was the constant term. You knew that the y-intercept on a line happened to also be the constant term when we were writing it in y equals mx plus b, right? Y equals 3x plus 5. That 5 was your y-intercept. So in both the line, the constant term was the y-intercept, and in the quadratic, the constant term was the y-intercept. Well, that's actually a pattern you're going to see for all polynomials, okay? So what we want to do is we want to take some of that knowledge that you already have and apply it to any degree, okay? So grade 10 was all about degree 1, grade 11 was all about degree 2, grade 12, now we're going to go degree 3 up to infinity. Doesn't matter. Okay, because they all share the same characteristics. They just get a little messier as the degrees get higher and higher and higher. Okay. Quick review from your last lesson. Now, this is not in your book, but I just want you to think about it for a sec. Consider the functions f of x equals x plus a over x plus b. Sorry, x plus a over x plus b. Sorry, I paused there because I looked up at my screen to make sure I was recording because I didn't actually remember pressing record. And then I thought, have I just been talking to the air for the last couple minutes? Anyway, I'm recording, it's all good. So let's try this again. Consider the functions f of x equals x plus a over x plus b. G of x is x plus a over x plus b, x plus c. And h of x is x plus a, x plus c over x plus b, x plus c. A, b, and c are all different real numbers. Now, which pair of functions, this is a great little test question, which pair of functions do you think the graphs will have graphs that appear to be most similar to each other? So you can pause me for a sec if you want and talk about it with each other. Okay, and your answer should have been, well, take a look at this guy. We've got f of x and h of x. The only difference between f of x and h of x is I've got a point of discontinuity at x equals negative c, right? When you see this guy here, let me just circle that for you, or highlight that for you. This guy simplifies out mathematically, and if it simplifies out mathematically, I'd actually be left with f of x. But remember, when we simplify those factors, and remember, I don't want you to write it in simplified form because then we lose the fact that there's a point of discontinuity there. But when we have that shared factor, that creates that little hole in the graph. So the only difference, these graphs would look exactly the same, except that the h of x one would have that tiny hole for the point of discontinuity. Okay. All right. With what common characteristics will all three graphs have? Well, again, you can pause me for a sec if you like. X plus a, x plus a, x plus a is always on top. So that's going to be a x-intercept at negative a comma 0. What else do we have? We've got x plus b is always on the bottom. So I'll have a vertical asymptote at x equals negative b. okay? All right. So here we go in polynomials. Now, again, this is still not in your notes, so don't look for it. F of x equals a to the n of x to the n plus a to the n minus 1 of x to the n minus 1. And some of you guys are like shutting down now and you're like, whoa, that looks confusing. It's not. The purpose is to say I start with the highest degree and the coefficient that goes with the highest degree, and then I just keep going down in degree until I get to 1. So if I wanted to create a degree 6 polynomial, I would have to have y equals whatever, 7x to the 6th. That is now a degree 6 polynomial, okay? But then if I wanted to keep adding stuff to it, minus 3x to the 5 plus 2x squared plus 1, okay? Now I skipped some terms here, but it's a degree 6 polynomial because I have the leading guy has a degree 6 on it, okay? What's not allowed in a polynomial is you can't have fractional exponents on your x value and you can't have negative exponents on your x value. If you had fractional exponents on your x value, you actually have a radical graph. If you have negative exponents on your x value, remember that would send it to the bottom of a fraction, which means you actually have a rational graph, and we've already talked about both of those, okay? The end behavior describes the behavior of the y values as the function of x becomes very large. So we're looking, usually we're looking to the right, okay? Sometimes we may also describe the end behavior like this. So if I gave you a graph, I'm just gonna switch to brown here for a sec. If I gave you a graph that looks like this, okay, we could say the graph ends going up, okay? We could also say the graph starts in quadrant 4 and ends in quadrant 1. Okay, that's another way we could describe this graph because we read the graph left to right. Okay, so it's as we come into the window, we're coming in on, sorry, I said quadrant 4, quadrant 3. 1, 2, 3, 4. So we're coming in on quadrant 3 and we're going out on quadrant 1. Okay. We could also say it from a calculus perspective, and a calculus perspective would say the different, what's happening to y as x approaches positive or negative infinity. So just to give you a little calculus note here, we could say as x approaches, that's that arrow, okay, as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity. Okay, so as x approaches infinity, y is shooting up. And as x approaches negative infinity, y is shooting down. Okay. For the most part, though, in 30-1, we're happy with you looking at this graph and saying the graph ends up. Okay. Okay, polynomial functions are continuous, so that means that I can write the whole thing without lifting my pencil. Remember, I couldn't do that with rationals because of those asymptotes. I had to lift my pencil to get on the other side of the asymptote, okay? The solutions to a polynomial equation are the x values that make y equals 0, also known as the roots of the equation or the x-intercepts. And you've been solving for those in lines and in quadratics all the time. We will take you higher than degree 2 in 30-1, but a lot of the process will remain the same. Polynomials are named based on their degree, which I've already talked about. I had written a degree 6 up there a couple seconds ago. And the degree of the polynomial is the highest exponent located on the leading coefficient, okay? Now, remember, coefficient is the number that goes in front of the variable, so the leading coefficient is the very first number if we have written the polynomial in order, okay? So what can you tell me about this graph? Do you say that this graph ends up or down? You should automatically say that graph is ending up. And maybe your answer to that right now would be because I have a positive slope, right? That 3 is your slope. Well, now I want you to think about the fact that, yes, this is a line, but this is a polynomial of degree 1. The leading coefficient is positive, okay? And it's the leading coefficient being positive that actually tells you you end up. What if I asked you about this graph here? I'm going to give you a quadratic this time, and I'm going to go, we'll just leave it like that. Okay, and I would want you to tell me that that quadratic ends down, or opens down, right? And maybe you don't like that I didn't write it in standard form, so that's fine. If I do this for you, I just don't want anyone to be mad at me or anything. 2x squared minus x plus 4. Doesn't really matter. Either way, I want you to look at that and say that quadratic ends down. Well, here's a polynomial of degree 2, and the leading coefficient is now negative. Okay? Okay. Cool. So what I've done here is I've just given you some general pictures of different degrees. So you have degree 0, which you probably can't see there because it's behind me. So I'll just draw behind my video, I'll just draw it on the board for a second. A degree 0 is just a horizontal line, okay? And then you have a degree 1, degree 3, degree 5, and then I've shown you a degree 2 and a degree 4. There are names for these guys. 1 and 2 you're familiar with, linear and quadratic. When we get into degree 3, we call it a cubic. Degree 4 is quartic, and degree 5 is quintic. Now, there are so many things we want to talk about here. First thing I want to do is just take a look at how it behaves, okay? So for instance, all my odd degrees are essentially behaving like a line. Okay, now they're not a line, obviously, but what I'm trying to say is if I connect those two endpoints together, they're going to behave in that general shape of a line with a bunch of funky stuff happening in the middle. Okay, the degree 2 gives me that parabolic shape, but the degree 4 also behaves generally parabolic like that. Okay, there's just funky stuff happening in the middle. So any odd degree is going to have similar properties to a line, and any even degree is going to have similar properties to a quadratic or a parabola, okay? Okay, the other thing I want to talk about, degree 1, how many x-intercepts do I have? 0. Degree 2, I have 1, sorry, this is degree 3. Degree 3, 1, 2, 3. Degree 5, 1, 2, 3, 4, 5. Degree 2, 1, 2. Degree 4, 1, 2, 3, 4. Okay, so now some of you are looking at that and saying, oh, the degree tells me the number of x-intercepts. That's actually not true because look, you guys have dealt with this last year. Think about a quadratic here. This is still a degree 2, but there are no x-intercepts, right? So the degree does tell me the maximum amount of x-intercepts. Okay, I also want to talk about something called turning points while I have these diagrams up here. Turning points are where I change direction. So degree 1, there is no turning points. Degree 2, here's a turning point, here's a turning point. Sorry, degree 3, I have 2 turning points. Degree 5, I have 1, 2, 3, 4 turning points. Okay, degree 2, I have 1 turning point. Degree 4, I have 3 turning points, and now you're saying, oh, okay, the number of turning points will always be 1 less than the degree. Okay, the number of turning points will always be 1 less than the degree. Okay. So what I want you to do is we're going to work through these tables together, and we're going to try and fill in the table and draw a little picture of what we're looking at. Now the goal is, as I walk you through this, I want to see how much you can fill in without looking at a picture of the graph first, okay? Again, I'm not saying that to stress you out. Nobody's going to take your graphing calculator away from you, but the more you can kind of struggle with the visual in your head, the deeper an understanding you're going to have of this, okay? So polynomial function in simplified form is f of x equals 1/2 x minus 10. You have been doing that for 3 years now. It's a first degree because the exponent on the x is just a 1. The number of x-intercepts will be 1. The y-intercept will be at 0, -6. We know that because of we would have called it in grade 10 the b value, right? Y equals mx plus b. Now I'm going to shift our focus to say, isn't that just the constant term? That is the number that's by itself without a variable, okay? The end behavior, does this graph end up or down? Your answer is up, right? Because I have a positive slope. So you're looking at this number, which is the leading coefficient, and you're saying, hey, that's positive, my graph is ending up. The number of turning points will be 0 because it's a line, I don't turn at all. Okay, and then the drawing, well, I know I started the y-intercept at -6, and I'll go up 1 over 2, up 1 over 2. So this is what you should have for that one. Okay, next one, pause me and try this yourself. Okay, so the degree is 2. The number of x-intercepts, well, I know this graph opens down. I know I have a leading coefficient of -2. That tells me the graph opens down. My constant term is 4, so that tells me the y-intercept. You may or may not be comfortable trying to figure out how many x-intercepts there are right now. You could graph this. So you'd be looking for two numbers that multiply together. You could factor it, sorry, you could, let me try that again. You could graph this and just take a look at them. You could try and factor it or try and use the quadratic formula or try and complete the square. Those are all things that you did in 20-1, okay? The y-intercept is the constant term here, which is 4. The end behavior, this is going to end down. So this is going to be a parabola that opens down, and the number of turning points will be 1. Okay, and so there are two x-intercepts. And again, you could have done that by graphing or by factoring or by some sort of strategy. Right now, I just want you to understand that there are two. I'm not as concerned right at this moment that you tell me exactly what they were, okay? Okay, next one. Okay, so now we're getting into a cubic graph. You see that x to the 3. So that's a degree 3. The number of x-intercepts, well, I know I'll have a maximum of 3, but I probably want to put this one in my graphing calculator. I don't know any other strategy to figure out how many x-intercepts are there as of yet. We're going to talk about that soon. So plug that one into your graphing calculator and check the number of intercepts. The y-intercept will be at 0, -2, because that again is that constant term. The end behavior, is this graph going to go end going down or end going up? Well, again, we're looking at that leading coefficient. So the leading coefficient is negative right here. And so the graph will end going down. The number of turning points, remember we talked about, pardon me, the number of turning points is always one less than the degree. So if this is a degree 3, there should be 2 turning points in it, okay? And hopefully by this time you've already graphed it, and you can verify that with your graph. Okay, and then the number of x-intercepts in this guy was only 1, okay? So remember, the degree of the polynomial tells us the maximum amount of x-intercepts that we can have. You could foresee, had I shifted this whole graph up, just to have that conversation with you, had I shifted this whole graph up right around here, I could have got 3 x-intercepts if that was the x-axis, right? Okay, cool. Okay, try this guy. Again, as far as the amount of x-intercepts, you're gonna probably have to graph it. So we have a degree 3. We have number of x-intercepts is only 1 again here. But again, you can see right below there, had I had the x-axis right around here, you could have gotten 3, okay? Had I had the x-axis right around here, there was a possibility to only get 2, okay? But for this guy, it happens to be just 1. No way to get 4 because the degree of the polynomial is the maximum amount of x-intercepts that you can have. Okay, my y-intercept, I saw that in the equation as my constant term, so that's at 0, -2. A reminder, when you're asked for the intercepts, they have to be a coordinate pair. They can't just be a number. They have to be a coordinate pair. Coordinate pair has to have brackets around it. My leading coefficient here was positive, and we notice that this graph ends up, okay? And then again, the number of turning points were 2. I have one right here and right here. Okay, now try this guy. So even without the graph, without the aid of my graphing calculator, I know the degree is 3. I know the y-intercept is at 0, -36. I know my end behavior will be going up because I have a positive leading coefficient. I know I'll have 2 turning points because it's always 1 less than the degree. But now graph it and figure out the x-intercepts, figure out the general shape of the graph. And we ended up with 2 x-intercepts on that guy. Okay. All right, try this guy. Make sure you're pausing me and trying things yourself. You're going to end up with, this is still a degree 3. The y-intercept will be at 0, -10. The end behavior will be down this time because my leading coefficient is negative. There'll still be 2 turning points. You'll graph it to find the number of x-intercepts. And in this one, we get 3. Okay, good. So figuring all that out and putting all that together, let's take a look at this next table. So now I've given you a graph and we want to try and figure out some things. The degree, well, let's go by turning points for a sec. I have 1, let me draw those in for you. I have 1, 2, 3 turning points. So if that's 1 less than the degree has to be 4, okay? Sign of the leading coefficient, well, am I going up or am I going down at the end of this, right? We're not looking at the left right now, we're looking at the right as x approaches infinity. And I'm going up, so I'd have a positive leading coefficient. The constant term, well, the constant term would be, let me just take that ink off. It would be right about there, right, on the y-intercept, so 4.5. End behavior is, it's ending up. We already talked about that one. The domain. Now remember our conversation about computer-generated graphs. This is a computer-generated graph that spills off of the window provided. The window stops right here. Okay, so because of that, you know that this will go in this pattern forever and ever and ever. If you have a hand-drawn graph and you want to specify that, you have to put arrowheads on it. But on a computer-drawn graph, you do not need arrowheads. It just needs to spill off the page. So the domain for this is going left forever and right forever. So it will be a member of the reals or from a negative infinity to infinity. And the range will be greater than our bottom. We have an absolute bottom here at -5. And so the range will be greater than -5. Okay, so just take a look at this, and that's what you should have in for everything. Okay, try this guy. So we have the degree here, we have 2 turning points. So it'll be a degree 3. The sign of the leading coefficient is going to be positive because my end behavior is going up. Okay, so I kind of answered those 2 at the same time. Constant term here is at -1. The domain will be real again, and the range actually will also be real because this is going to go down and go up forever. Sorry, I think I said -1 there. If I'm wasn't looking super close, it's a little more than -1, so that's why I said -1.2 there. We would make that obvious, or we would accept an estimation for that. Okay, try this guy. 1, 2 turning points, so it's degree 3. Sign of the leading coefficient, well, this graph ends going down. That's the end behavior, so the sign of the leading coefficient has to be negative. The constant term, I'm going to look a little closer here. Looks like it is right on 6 this time. Domain will be real, and range will be real. Okay? You got this. Okay. So the last sort of thing we need to talk about in this note is multiplicities of zeros. Now, don't let that sound confusing to you. When I'm talking about a 0, I'm talking about an x-intercept. Okay, multiplicity of zeros refers to how many times the same x-intercept is going to appear in the question. For instance, okay, if I wrote y equals x minus 1, okay, you would tell me that the x-intercept there is 1, okay, and you would tell me that that x-intercept technically appears once. So that we call that a multiplicity of 1. Kind of boring. But then, what if I said y equals x minus 1 squared? You would still tell me I have an x-intercept of 1. The thing is, this actually means x minus 1 times x minus 1. So I actually have 2 x-intercepts at 1. Okay, now there's still just that one x-intercept. What happens is there's two roots, but there's one x-intercept. So there is a small difference between what we would determine to be a root and what we would be determining to be a x-intercept. That's why often we would say, how many different x-intercepts are there or something like that, okay? So it's like there's two of them here, but they're directly on top of each other. Now, that changes the behavior of the graph. It changes how the graph intersects the x-axis, okay? And there are essentially three scenarios that we have to deal with. We have to deal with an exponent of 1, an exponent of 2, and an exponent of 3. So I'm just going to quickly read this with you. Multiplicity of a 0, or x-intercept, is the number of times a 0 of a polynomial function occurs. Different multiplicities will change how the graph behaves with respect to the x-axis. To find the multiplicity of a 0, look at the degree of the factor of the 0. So here, the degree of this factor was 1, and here, the degree of this factor was 2, okay? All right, so let's figure out the equation in factored form here. So essentially what I want you to do is play in your graphing calculator for a second and see if you can get a picture of this, okay? So we don't know what a is, that's okay. You can just leave it as 1. But I want you to write x plus 2 to some exponent, and I want you to write x minus 1 to some exponent, and I want you to play around with the numbers there until you can get a picture that looks like this, okay? I'll make it a little easy if you're stressed out. Play only around with exponents 1, 2, or 3, okay? Okay, and so you should have found that what worked was x plus 2 cubed and x minus 1. So the x plus 2 cubed gave me this funky looking shape here, okay? Now, that is a very funny way to behave. I'm not going straight through. I'm not turning around. What I'm doing is something called inflecting, okay? This is called a point of inflection right here. And so what happens is the graph will curve into the x-axis and then curve out of the x-axis, but I don't actually ever change direction, okay? So that guy there is called a point of inflection. On the other guy, the 1, I just went right through, okay? All right, so try this guy. I'm giving you the equation. You have to now figure out what exponents would go there. So play on your graphing calculator for a minute. Okay, so up here, probably you had a good guess that that's a point of inflection. So that would be the x minus 2, so you should probably have a 3 there. Here, I went straight through, so that should be a 1. So this guy here would be a 1. And then here we haven't talked about yet. There I changed direction. Okay, well, if I change direction, it's not going to be a 1 and it's not going to be a 3. And if you were paying attention, I told you only to play with 1, 2, and 3. So hey, it's going to be a 2. Try that guy. Okay, all right. So now we look at this question, and we're going to be trying to draw this without a graphing calculator. Now, just to summarize, you're going to summarize this whole multiplicity conversation in a second. But there are 3 different ones that we do. We had a multiplicity of 1, a multiplicity of 2, and a multiplicity of 3. If I had a multiplicity of 1, the graph went straight through. If I had a multiplicity of 2, the graph changed direction. And if I have a multiplicity of 3, that's where I have that point of inflection, okay? Now, if you're curious, because I know you are, check out 4. Go in your graphing calculator and just write x minus 1 to the 4, okay? Make sure there's brackets around x minus 1. Check out 5. Check out 6. What you notice is that any even multiplicity will look like this, okay? And any odd multiplicity except 1, so any odd multiplicity higher than 1 will look like a point of inflection, okay? So we're going to take a look at this equation together, y equals negative x plus 2 squared and x minus 1 cubed. And we're going to try and figure out what we could do to draw it, okay? So what do I know? Well, I know I have x-intercepts at -2 and at 1 because of the factors here. So I could plot those points. I know I could figure out a y-intercept by plugging in 0 for x. So if I plugged in 0 for x, this would give me 2 squared, which is 4. -1 cubed is -1. 4 times -1 times -1 would give me +4. So I have a y-intercept of +4. Okay, so we'll write that stuff down. I have an x-intercepts at -2 and 1, y-intercept at 4, and then we can plot those points. Okay, I know that my end behavior is going down because I have a negative coefficients. Okay, so right away I could say, okay, I have to end going in this direction. I know that this is a degree 5 altogether because the overall degree of a polynomial will be the sum of the multiplicities. Okay, think about this. If I was to multiply this out, right, because I read the degree when everything's written in general form, so it's like that big long chain with the highest degree all the way to the lowest degree. If I was to multiply all this out, at some point I'd have to multiply an x squared and an x cubed together, and that would give me an x to the 5. So I know that this is a degree 5, which means it's an odd degree, which means I need to sort of behave like a line. So if I'm coming down here, I would have to be going up on the other side there, right? So that it would join a line. And so now I have to join these, I have to join all these 3 dots thinking about multiplicity. So here I come, I'm heading down to my x plus 2 squared. At that point, I need to change direction because of the multiplicity of 2, okay? Which is great because that's the only way I'm gonna hit the y-intercept. So at some point I need to come up and go through the intercept, and then I'm gonna have to change direction at some point to come back down. And then at 1, what do? I have to inflect. So I'm gonna curve around and inflect. Hey, that wasn't actually that bad with a mouse. Okay, so my graph looks something like that. Okay, now what you can't tell me when you're drawing these things is you can't tell me exactly where this point is or how high it goes, okay? But you can get a pretty decent sketch of what's happening. Those of you coming to calculus, we will be able to algebraically determine that in calculus. That'll be fun. Okay, so just gonna clear that. And so the leading coefficient is negative. I got a little ahead of myself here. The leading coefficient is negative, so the graph ends down. At x equals -2, the graph will change direction because of the multiplicity of 2. And then at x equals 1, the graph will inflect because of the multiplicity of 3. That's a typo there. That should say 3, not 1 there, okay? And so there's a good computer drawing. So that is the actual one. So if you compare that to the one I did, I actually had my, my maximum point on the other side of the y-intercept. Again, you would have no way of knowing that until you actually graphed it, okay? What we're looking for when we're asking you to sketch this is, can you put together your knowledge of multiplicities, of leading coefficients, of x-intercepts and of y-intercepts to get a general picture, okay? So don't stress about the exactness of that point up there. Okay. Now we're going to try this guy. Well, we're going to walk through the same sort of thing. At x equals -c, which means I'm on the left of the, like, just think about transformations there. If that says x plus c, I'm going to be on the left side of the axis, and I'm going to change direction. I've got intercept at B where I'll go straight through. Okay. So x-intercept at B on the right goes straight through. X-intercept at C on the left changes direction. Leading coefficient is positive, so it should end up. You were told in your book, I'm just looking at your book here, I didn't write it in the PowerPoint, but you were told in your book that A, B, and C are all positive numbers. That's how we know that, okay? I will add that to the slide here just to avoid confusion, but that is why we know that the leading coefficient is positive, okay? Do you see where I am in your book? Okay. Okay, so we're gonna draw that, and we should get something that looks like this, Okay, again, I'm looking for the general shape. I'm looking for the fact that you ended up. I'm looking for the fact that you went straight through on any positive number here, right? I didn't actually say it was 2, I just said it was a positive number. I'm looking that you change direction anywhere on the left of the y-axis, okay? All right, so now we're gonna summarize everything we've just learned. The degree of an individual root determines the multiplicity or behavior of the graph at the x-intercept. A multiplicity of 1 will go right through the axis. Multiplicity of 2 will touch, that's called the point of tangency, by the way, when we touch once and only once. So sometimes you'll hear it say the graph is tangent to the x-axis at that point. And then a multiplicity of 3 will inflect, okay? Okay, the maximum number of x-intercepts a graph may have is equal to the degree of the function. The maximum number of turning points will be 1 less than the degree of the function. And the blank of the equation of a polynomial function indicates the end of the end behavior of the graph. So the leading coefficient, whether the leading coefficient was positive or negative. If the leading coefficient was positive, I'm ending up. If the leading coefficient is negative, I'm ending down. The constant term in the equation of a polynomial is the y-intercept of the graph. For an odd degree, as x approaches plus or minus infinity, the values will head in opposite directions. So as x approaches infinity, y will approach infinity, but then as x approaches negative infinity, y might approach negative infinity. So that's where I was talking about it kind of behaves like a line with funky stuff happening in the middle, okay? And then for even ones, as x approaches positive and negative infinity, they'll head in the same direction, either going down or going up, okay? Yep. Okay, that's it for me. You're gonna work on pages 95 to 103 now, so your goal is to get up to 103 before we talk about the remainder theorem and factor theorem, which we're gonna do tomorrow. So we're gonna go back to that conversation around polynomial long division tomorrow, okay? So try this stuff out, and if you have any questions, please don't hesitate to get in touch with me, okay? Have a great day, guys.